All right, welcome to lab for today. So a little sparse on people today, but that's okay. It's lab, so we'll make it. So this is our second to last lab. So we got this one, and then the one on Monday, and then that'll be it for the lab portion. So basically today we're going to start our two labs having to deal with light. So let's talk a little bit about those. So as we talked earlier in the semester, we know light is an electromagnetic wave. And since it's a wave, that means it's going to satisfy all those same properties of waves that we talked about earlier in the semester, all that stuff that Katie didn't like. So that'd be great. Okay. So having said that, so what that means is it's going to have a wavelength, it's going to have a wave number, it's going to have an angular frequency, it's going to have all that different stuff. And it's also going to behave like a wave. So for example, we can have a wave encounter a boundary. And as we talked about earlier in the semester, when a wave encounters a boundary, two things are going to happen. Part of that wave is going to be reflected. So for example, this is my incoming wave. So here we're using is what's known as a ray diagram. So let me write that on here. So ray diagram. So what a wave diagram is, or ray diagram is we'll talk more about this in the semester, in the class, but if I have a wave, which is say, these are the wave crests, so that this distance across here is the wavelength, then what a ray is a vector which points perpendicular to these wave fronts and points in the direction of the velocity of the wave. Okay, so this is what we call a ray diagram. So here, we're imagining then is that what we have a incoming wave which is coming in, which I'm going to classify by this ray diagram. So this is my initial incoming ray, and that's going to strike our boundary at an angle of θ1 relative to the normal. So this angle here is 90 degrees. So this is what we call the normal. So part of that wave is going to be reflected. So that's the green line here. So part of it's going to hit and get reflected off, and that's what we call the reflected wave. The other part then is going to be transmitted or refracted then into the second medium. So initially it's moving in medium 1. It's going to go into medium 2. So some portion of the wave is going to get refracted. The other portion is going to get reflected. Now, depending on the type of wave and the type of materials, like for example, if this was a mirror, 99% of it's going to be reflected, and then only like 0.01% is going to be refracted. So if it was a mirror, but different materials and different mediums have different amounts which are going to be reflected and which are going to be refracted. So for the reflected wave, we have what's known as the law of reflections. What the law of reflection says is that if the incoming wave comes in, strikes the medium and gets reflected back, then the incoming angle θ1 versus the reflected angle θr are actually exactly the same. So this is what's called the law of reflection. So the law of reflection says that the incident angle is equal to the reflected angle. So this is what we call the law of reflections. In this lab, though, we're going to be paying attention mostly to the refracted portion. So we need to know what happens for the refracted portion. Well, what happens for the refracted portion is anytime light travels in a different medium, that different medium has different dielectric properties to it. So you can basically think of mediums as they're moving, the wave is moving in as different dielectrics. So here I have a dielectric. Here I also have a dielectric, but I have two different dielectrics. So this has some dielectric constant. This has a different dielectric constant, which means that this has what we call an index of refraction. So this is going to have some index of refraction of N1, where this one has an index of refraction of N2, which is related to the dielectric constants. So this is related to the dielectric constants. So the different mediums then again have different dielectric constants, and those different dielectric constants will give rise to what we call an index of refraction. So the index of refraction comes from the fact that the wave is now moving within a dielectric. So since the wave starts moving within a dielectric, basically what happens then is that its speed gets reduced. So the speed at which the wave travels then with inside of the dielectric now gets slower than the speed of light. So here we have c, which is defined as the speed of light in vacuum, which is about 3 times 10 to the 8th meters per second. But when it's moving inside of the dielectric, what happens then is that the speed gets slower by amount of the dielectric, or the index of refraction. So the speed at which it moves within inside of this medium then is going to be the speed of light divided by the dielectric constant, which means then that the dielectric constant is defined then as the speed of light divided by the speed at which it moves within inside of the medium. So what this does then is when it moves from one dielectric constant to another dielectric constant, or from one medium to another medium, or from one index of refraction to another index of refraction, what happens then is that the light ends up either bending towards the normal or away from the normal, depending on the ratio of these two dielectric constants. So meaning if it goes from, say, a high dielectric constant to a low dielectric constant, or from vice versa, from a low dielectric constant to a high dielectric constant, the light then is going to get bent. So what the law of refraction says, which is also known as Snell's law, says that the way that the light is bent depends on these dielectric constants, or on these index of refraction. So Snell's law, which is also known as the law of refractions, says that when it's moving inside of medium 1 with index of refraction n1, then n times sine of theta 1, where theta 1 is the angle incident of that incoming ray relative to the normal, has to then be equal to n2, which is the dielectric constant, or the index of refraction within inside of medium 2, times sine of the angle 2, which is the angle at which it is then being bent at inside of the second medium. And again, this is relative to this normal down here. Okay? So this is what we call Snell's law. So Snell's law simply says that this index of refraction times sine of the angle must be equal to this index of refraction times this sine of this angle. Right? So this is what we call Snell's law. So basically what happens is it's going to travel different paths inside of different mediums, because what light wants to do is it wants to minimize the amount of time it spends within inside of this medium. Right? Now what also happens is, in general, these index of refractions are also actually frequency dependent, which basically means that different wavelengths of light are going to bend differently, which is actually what creates a rainbow. And we'll talk about this in class, but what we actually see as rainbows are when light enters then a rain bubble, right? So a rain droplet, a water droplet. What happens in that case then is white light, which is a superposition of all possible wavelengths, gets split up because each different wavelength is traveling a different distance and gets bent differently inside of the water droplet, which causes it to disperse. And then it gets reflected off the back wall, and then it gets reflected back into our eyes. So actually this is what's responsible then for a rainbow. But again, I'll show you pictures of that, and we'll talk more about that later. So basically this is all we're gonna be doing in this lab. So in this lab, we're gonna do is we're going to be looking at the refracted wave. So again, we're gonna take a surface here. We're gonna send in an incident beam. We're gonna measure then its incoming angle, theta 1. And then we're going to look at the refracted beam, so as this guy gets refracted down, and then measure the angle theta 2, and then try to determine what is the index of refraction of the medium. So here, we're going to be using index of refraction n1 equal to 1, which is air. So this guy's going to be moving in air. And then from here, we're going to be trying to determine what is n2. Okay? So to do that, we're going to use this PHYS simulation. I just sent everybody an email a little while ago with the link for this, just in case the one in the lab doesn't work. So basically, we want to have this clicked on ray, so not wave, but we want ray. So we're going to draw these ray diagrams. It's going to look something like this. So from here, you're going to pull out your protractor. So go ahead and line this up so that the 0 is along the normal line here. So this is our 0. Good. And initially, we're going to have this thing set to water. So the material in index or refraction, again, here 1 is going to be 1. Medium 1 would just be air. Medium 2, we're going to go with water, and we're going to know the index of refraction is 1.33. Okay. So from here, we're going to go ahead and turn this on, and we're going to measure then, we're going to move the incident ray, so it's at 30 degrees. So this is at a 30-degree angle relative then to the normal. And then down here, I simply want to measure this angle. So if I was measuring this angle, I'd measure it maybe about 22 degrees. Then we're going to move this guy to 40. And then again, I'm going to measure the refracted angle. And then I'm going to measure it at 50. And then again, I'm going to measure the refracted angle. So from here, we're then going to use Snell's law, where again, Snell's law says that sine of theta1 is equal to n2 times sine of theta2. And here I'm just saying that n1 again is equal to 1 because that's air. So that n2 will then be equal to sine of theta1, which is the incident angle, divided by sine of theta2. So from here, you're going to calculate then 3 different n values for each one of these 3 different sets of angles. Right? So from here, you'll have 3 different n2s, and then average, and then discrepancies. Okay. So from there, then we're going to do the same thing again. So let me arbitrarily put this somewhere. And now we're going to switch material of the second medium to now mystery A. So now we don't know what the material is. So we're going to do exactly the same thing. So again, I'm going to put this at 30 degrees. I'm going to measure the refracted angle, go to 40 degrees, measure the refracted angle, go to 50 degrees, measure the refracted angle, and then do exactly the same thing. So again, I'm going to calculate n2 by taking the ratio of the sines of the incident angle to the refracted angle. Again, come up with 3 different n2 values, take an average. For this part, though, we can't do a discrepancy because we don't know what it is. Right. So for the mystery one, so for mystery A, no discrepancies. Okay. So good. So finally, we're then going to go to the bottom part here, and then we're going to click on Prism. So now we're going to go to a prism, and then we're going to go and pull out this guy, which is our triangular prism. Okay. And then basically we're going to do the same thing. So we're also going to pull out the protractor. I said pull out. Okay, maybe if I just click on it. There we go. I just got to click on it. So good. So from here, we can move this guy around. So again, we're going to do basically the same thing. So from here, I'm going to go ahead and shine the laser inside. Okay. And then from here, I want to turn on the normal lines as well. So from here, we're basically going to do the same thing. So you want to rotate your protractor, and then again, try to line it up so that the normal line is along, or at least the 0 is along the normal line. Okay. So from here, then you want to, again, measure this angle here. So again, this is maybe 31, 32 degrees. So this is your incident angle. And then measure this angle across here. So this is going to be your refracted angle for this side. And then rotate it. And then measure it again across on the other side. Whoops, moving my stuff here instead. Protractor move. Okay. Anyways, now move the protractor. Get rid of the protractor and put it back in. So now you're going to move it to this surface over here, and then again you want to measure an incident angle on this side with the refracted angle on this side. Okay. Now for this one, the incident angle is now going to be with the index refraction of the glass, where on this side the refracted angle is going to be with the index refraction of n is equal to 1 because it's now going to be refracted into air. So basically, from here, you want to then use Snell's law across this boundary, use Snell's law across this boundary, and then try to find the index refraction of glass for this boundary here as well as this boundary here, which again is going to give you 2 different index refractions. So you're going to have one from this side, one from this side, and then again, average those 2 together, and then using that the index refraction of glass is...
Daddy, I just came back from karate class.
You did not just come back from karate class.
But
Anywho, so then you want to compare that to the index refraction of glass and then find it. Hang on a second. And then find its absolute and relative discrepancies. Okay, so basically the same thing. So again, the only difference is here, you're using this twice. The only difference is, again, when you're looking at the prism, so in the prism here, So here, this incoming light here, this is your first medium. So here, this is going to have N1 equal to 1, where this is going to be N2. But then for this wave coming on the inside, your incident 1 corresponds to N2, where your refracted 1 now corresponds to N1. So basically, this ratio is just going to shift. So it's going to be inverted from each other. But again, for here, you're going to calculate this N2 here, as well as this N2. So in this case, you'll have 2 N2s. And then from there, you want to, again, find its average, and also, again, its discrepancies. Discrepancies. Again, comparing that to glass. And that's pretty much it. So that's it.
Could you repeat how to do, like when you were looking at this, what we're actually recording?
Oh, sure. So here you're recording 4 angles on this one. So for this one, you're originally going to line it up so that this is, so if I rotate this guy here, let's see, let me try to put this back to where I had it. So that this is my initial, so basically I'm measuring this angle here and this angle here. So this is my initial angle. This is then my refracted angle. Then I want to measure it across this boundary over here. And so let's see if I can actually get this thing moved. The problem is I can move that, but I can't move this. There we go. Let me move that out of the way. Let's put that back here. So good. So now I'm going to rotate this guy to this side. And now I want to line it up so it's against now this boundary here. So good. So I'm going to put this guy here. And now I'm going to measure this angle here. So this is now my new incident angle. And then I want to measure this angle here, which is now my new refracted angle. So basically, I'm measuring 2 sets of incidents and refracted angles. So I'm measuring incidents and refracted on this side, incidents and refracted on this side. So that way I'm going to use Snell's law across this boundary and across this boundary separately.
Okay, so the dotted line is the boundary line, so that's...
Okay. Well, the dotted line is not the boundary line, but it's the normal line. So that is the line at which you are taking the angle in reference to.
Okay.
Okay. So the boundary line is simply just the line of the prism itself. So that is the boundary. So the normal line here is the dotted lines. So those are the lines that I'm taking the angle in reference to. So let me draw it on a different page so you can kind of see a little bit better. Let me do an overly exaggerated prism so you can kind of see a little bit better. So let's say my line is coming in here. So this is my normal line. And then this is going to be my incident line coming in this way. So this is my incident ray. Okay. So basically I want to measure this angle here. This is going to be, let's call that theta 1, well, let's call it theta incident 1. Okay. Okay. So this is then going to refract. So this is going to refract then something like this. Okay. So then I want to measure also this angle here. So this is going to be my refracted angle 1. Okay. So now on here, this is now my normal line going in this direction. So this one, which was the refracted one, is now the incidence according to this boundary here. So now what I want to measure is now this angle. So this is now going to be my incident angle 2. And this is going to refract, and then my refracted line is going to go something like this, which means that now I want to measure this angle here, which is going to be my refracted angle 2. Okay. So from here then, I want to now apply Snell's law across this boundary. So this is going to be boundary 1. And then apply Snell's law across this boundary. So this is going to be boundary 2. Okay. Oh, shut up. Okay. Always okay? So good. So here, for this boundary, you're just going to say, well, the incidence has index of refraction of 1. So I'm going to get a sine of theta incident 1 must be equal to N2 sine of theta refracted 1. Okay. Across this boundary, now it's coming from index refraction of N2, so now I'm going to have N2 times sine of theta incident 2 must then be equal to N over here, but this N is simply 1 because it's going back into air, and then sine of theta refracted 2. Okay. That's okay. So from this one, so for boundary 1, you're going to use this one to solve for N2. From this one, you're going to use this boundary and now solve this for N2 again. So you'll have 2 different N2 values. From those 2 different N2 values, you'll then average them together and then find discrepancies with index refraction of glass. So N2 should be the index refraction of glass.
Or it'll be that for both of those. That's what we're basing it off of.
Correct. Yeah,
okay.
yeah, because it's the same medium at which it's moving in. That's right. But you might get slightly different results because, again, you're trying to, so for example, if I'm measuring this angle here, I want to measure this entire big angle here. So assuming I have this lined up at 0 across here, that's going to be at what, 60, 70. And then here it's kind of hard to tell exactly what angle it's at. So there's going to be some, you know, variance in the angle at which you measure, but I might call that like 78 degrees. So when I calculate, I'm not going to get exactly the right answer just because, you know, again, this is kind of a thick line. So do I measure the middle of the line? Do I measure the side of the line? So there's a little bit of, you know, variance on how you're actually going to measure. Okay. Is that okay?
So the angle measurement is from the normal line to the refractor.
From the normal line to where the beam is, correct.
Okay.
So for this bottom one here, this would be from this normal line to that location.
Mm-hmm.
That's right. So measuring across this one, that would be, I don't know, maybe 36 or no. Yeah, 30 is what, where? So actually, no, that'd be more like 42 degrees on that side. And for this side, it would be like 78 degrees. But yeah, it's always measured from the normal line.
Okay.
And then the last thing I put on there was if you want to play, you know, try changing the color, and you can actually see that the refraction is different for different colors. So see how much it's being bent for different colors. So if you want, you can play around with it for different colors, and again, apply Snell laws, remeasure all your angles, and see if it still works out the same way, which it should, but that's fine. That was okay. And then looking at what I typed here, study using index refraction. I don't think that's the index refraction of glass. I think it's closer to 1.5. I don't know why I put that in there. Yeah, let me double check that. So it also depends on the type of glass, but that's fine. Yeah, so yeah, it should be closer to 1.5. So let me fix that and then I'll repost it. But yeah, so take it as 1.5. So index refraction of glass should be 1.5, not 1.33. Okay, okay, leave me alone. Okay, so as I said, so I'll change that here and then repost that. Should be 1.5. Great. Okay, there we go. So I'll repost that. So is everyone okay? A little bit clearer, hopefully. So yeah, so basically that's it. So that's all we're doing here. So again, for the first 2, again, you're just using the original parts. So let me go back to here. So again, you're just going to use the intro portion. And again, for the first part, you're just using water. And then in the second part, you're going to use then the mystery A. And then again, last part, just use the prism. Again, measure all those different angles. So here you're measuring 4 different angles by using 2 sets of 2 and then determine the index refraction of the glass there. Okay. Ooh, pretty. So actually, this is what I was talking about with the light. So actually you can see your rainbow here. So this was actually white light, which is coming in, goes in here, and this is actually what causes rainbow, is actually the dispersion, because each one of these different wavelengths have a different index of refraction, so they all bend differently. But so anyways, no side effect. So I'll stop talking. So any more questions anybody might have? Everybody's doing okay? So that's it. Not too bad. Not too bad. So for the first two parts, you're measuring 3 different index refractions, average those, discrepancy for the first one, no discrepancy for the second one. For the last one, you're measuring 4 different angles, 2 different index refractions, average, discrepancies. And that's it. And then Monday will be our last lab. So Monday we're going to play with optics. So basically play with lenses, so we can make things like glasses, so we can actually see things. And, telescopes and microscopes and all that kind of good stuff. So we'll talk about that on Monday. All right, so I'll be here, but I'll be here only until about 12:30, so about another hour instead of to the 1 o'clock, just because my wife had to miss her class yesterday, so she has to teach her class today. So I got to get done a little bit earlier, so because she comes up and uses the same room, and then somebody needs to watch our children, so that'll be my job. So it'll be great. So, okay, so like I said, if nobody has any questions, I'll be here for at least another hour, so feel free to ask questions and things. I'll just be doing more lab grading. I was doing that during the exam. It was either a choice of reading and reviewing a paper or doing lab grades, so I decided to do lab grades instead of reading somebody else's paper. So I'm a mean person. Okay, so anyways, have fun. I'll be here.